Okay guys, we're back. Concept 56.4. It says the Earth is changing rapidly as a result of human actions. This is the happy portion of our chapter. I say that tongue-in-cheek because it certainly is not good for the most part. The location of preserves today may be unsuitable for species in the future. So we were just talking about building, say, nature preserves or conservation areas, but what if, because of climate change or other aspects, the patterns of migration or the needs of those creatures shift to another area? What would we do if preserved locations had to shift due to climate change, especially if you have already built cities or human farms or whatever around those areas? You can't really shift the preserve to match where the animals need to live, and so that is just one aspect of one thing we might face in the future due to various actions of humans. Human caused changes in the environment we're going to take a short look at include nutrient enrichment, accumulation of toxins, climate change, and ozone depletion. One of the problems due primarily to human agricultural activity is what we call nutrient enrichment. In addition to transporting nutrients from one location to another, which we certainly do a lot of, humans have added new materials, some of them toxins, to the ecosystem. The harvest of agricultural crops exports nutrients from the agricultural ecosystem. When we harvest corn or harvest wheat, we're removing nutrients from that area and transporting them elsewhere. But agriculture also leads to the depletion of nutrients in the soil, as well as the addition of nutrients that weren't there before. Fertilizers add nitrogen and other nutrients to that ecosystem. So we have this whole mishmash of removing nutrients and putting in nutrients, and some of the nutrients we're putting in we sometimes put at too high of a level for the ecosystem to manage. So due to the use of fertilizers, pesticides and the like, that is how we have been able to sustain a population of 7 billion people on the planet. If we were still using the agricultural methods of, say, 200 years ago, we would not be able to sustain such a large population. Certainly wouldn't have been able to sustain that population growth, that almost exponential population growth of humans that was the case, for the last couple of hundred years. So the fertilization of corn, like you see here, the use of chemical fertilizers and applied fertilizers has been a benefit to humans, but not always a benefit to the ecosystems. When we talk about adding nutrients, we talk about something called critical load. It's the amount of added nutrient that can be absorbed by plants without damaging the ecosystem integrity. Nutrients that exceed the critical load can cause damage. So there will be a certain amount of nutrients that, say, a corn crop can take up. If we add more than that, we're going to have a problem. Oftentimes that problem comes in runoff, where you have rainfall or irrigation that causes that fertilizer or those nutrients or pesticides to go where they weren't intended to go. Agricultural runoff and sewage runoff leads to, among other things, phytoplankton blooms out in the oceans of the Atlantic and the Pacific, and then the decomposition of that phytoplankton causes dead zones due to low oxygen levels. So in a kind of a small area, let's imagine what might happen. So you have a farmer's field. He's applying liquid fertilizer to his corn crop. Right after he applies some liquid fertilizer, let's say there's a heavy rainstorm, and a lot of that fertilizer washes off of the field into the streams and into a nearby lake. Well, now there's a whole bunch of nitrogen available for the phytoplankton and the algae in that lake, so they grow like crazy. They grow so fast that they use up all of the various resources and they begin to die off. Now you have rotting algae, dead phytoplankton, all of that rotting material. As it decomposes, it pulls oxygen from the lake, and now suddenly you have fish dying off as well because there's not enough dissolved oxygen in the water. And so you have this dead zone or fish kill that you often see after a phytoplankton bloom. Enlarge that to include like the oceans themselves, and you kind of get the idea of the picture that we're talking about. Here's off the coast of our own state. Here's Texas here, of course, and Louisiana, and this red and orange indicate elevated levels of phytoplankton. In the spring and summer, when there's more rainfall, you get more runoff, and through the Mississippi River and all the various rivers that flow to the ocean, they carry large loads of nutrients, fertilizer and sewage runoff and the like. And you see in the spring and summer, you'll see this red band grow in size. That's a phytoplankton bloom, and that leads to dead zones where you have low oxygen levels out here in the coast of the ocean. As I mentioned earlier, unfortunately, it's more than just fertilizer that we add to the ecosystems. Oftentimes, from the use of pesticides and fungicides and herbicides, we add in various toxins as well. Oftentimes, these are synthetic chemicals that are lab created, man made created, unknown to nature prior to us creating them and then adding them to the environment. In some cases, these harmful substances can stick around for quite a long time in the ecosystem, and many of the substances become concentrated as you move up the food chain. So one of the reasons that toxins are harmful is that they become more concentrated in successive trophic levels. Think about the pyramid shape that we discussed as you move up from, say, the producers at the bottom of a food chain all the way up to the tertiary consumers at the top. This is called biological magnification, because as that material, that toxin that is part of the body of the creatures, as it's eaten by other creatures, the amount of toxin magnifies as it moves up the chain. Your textbook uses the example of PCBs, which are polychlorinated biphenyls, and many other pesticides such as DDT that are subject to this biological magnification as you move up the food chains. Thankfully, DDT is probably one that you've heard about or studied. Pesticide that was widely used years ago. Thankfully, its use is pretty limited since there has been an overall ban in the U.S. since the early 1970s, but it's still used in other parts of the world, and it still exists in ecosystems in other parts of the world. A good example is these herring gulls of the Great Lakes back in the 60s, 70s when DDT was still in use, or this is related to some of these PCBs, some of which are still in use. Herring gulls of the Great Lakes lay eggs with PCB levels 5,000 times greater than found in the phytoplankton. So these polychlorinated biphenyls that are consumed by the phytoplankton, which are then consumed by, say, shrimp and fish, and then are consumed by the gulls themselves, it concentrates the amount of that material into a smaller biomass. So then these birds are laying eggs that have huge amounts of this toxin material within the eggs themselves and within the offspring. So that's that biological magnification that we're talking about. Just a quick little picture here that kind of show you what we're discussing. So here ppm means parts per million. So you see it's fairly low in the phytoplankton, and then higher in the zooplankton, and then higher in the little fish, larger fish, all the way up to the herrings themselves, concentrating that material. In the 1960s, there was an author named Rachel Carlson. She brought attention to this biomagnification of DDT in particular. She was talking about a variety of pesticides, but DDT in particular was the one that was focused on in her book called Silent Spring. And shortly thereafter, in the 70s, DDT was banned in the United States. The 70s in particular were a strong time of environmental movement, kind of the beginning of the environmental movement, kind of the beginning of a lot of regulations, the creation of the EPA, the creation of the Endangered Species Act, and some of the varieties of regulations that are still in place to assist in preventing further damage to the various biological ecosystems of the world that we live in. Countries with malaria face a trade-off. Remember, I said oftentimes this gets sticky because there's all these various trade-offs and competing interests. Countries with malaria face a trade-off between killing mosquitoes, which are a malarial vector, and protecting other species. DDT is still commonly used in India, and it's a very effective pesticide. So that's why it's still used. I mean, it works. It kills pests very well, but it has these negative side effects, and so you have to weigh what is it worth, what are the benefits versus the downsides of using something like that. Here's a picture of Rachel Carlson. That book, Silent Spring, is oftentimes considered sort of the genesis of the environmental movement that really seriously began in the 70s and began the whole process of looking at what can we do to maintain the lifestyle that we want to maintain, but also perhaps try to do it in a way that is not so damaging to the environments around us. We're going to skip ahead to one of the other things that we need to look at, which is depletion of atmospheric ozone. So what we skipped over was global warming, and because that's been such in the news quite a bit lately, and it's probably more a topical conversation that might be more on your minds, we're going to cut off and take a quick break and then come back and discuss that one in a little bit more detail. So in addition to what we've talked about as far as adding nutrients and adding pesticides and chemicals to the environment, one of the other things that man has done is through his various activities he has depleted a lot of the ozone layer. Life on Earth is protected from the damaging effects of UV radiation, ultraviolet radiation, by this protective layer of gas called ozone. Ozone is a gas molecule. It's actually O3. So O2 is atmospheric oxygen, but when you have three of those molecules combined together, it forms a molecule we call ozone. And ozone has the ability to absorb and block ultraviolet radiation. So if life on Earth is down here on the ground with the atmosphere above, the troposphere, up into the stratosphere, there is a layer of O3 ozone that helps to counteract some of the damaging effects of ultraviolet radiation that normally streams from our sun. Satellite studies suggest that the ozone layer has been gradually thinning since about the 1970s, and that corresponds with the use of certain chemicals in our human lives. So here you can see the thickness of the October ozone layer over Antarctica, which it's most clear, this thinning at the poles, both North and South Pole. And here you can see the thinning of this layer has been slowly moving downward and then started to take kind of a tumble in the 70s, and then has kind of been jagged up and down since, and we're hopeful that this will begin to rise, and we'll talk about why in just a moment. The destruction of the atmospheric ozone results mainly from the use of what we call chlorofluorocarbons, CFCs, produced by human activity. CFCs are particular gases that can be used in refrigerators, air conditioners, so it's a major refrigerant, propellants for aerosols, cleaning solvents. They used to be very common. If you think about Freon, which is kind of the brand name of a particular CFC used in refrigeration, or like hairsprays that used to be in aerosol cans, all of those use CFCs. Well, the problem is these CFCs contain chlorine, and that reacts with the ozone to make oxygen. So it breaks down ozone into oxygen, and the oxygen does not have the ability to block and absorb the radiation that we're talking about. So this decreases the amount of ozone in the atmosphere. If we wanted to kind of look at a picture of that to explain, so up in the atmosphere we have the O3 ozone, which is what we want way up there in the atmosphere, but then there is chlorine that is introduced from these CFCs. There's a chemical reaction where the chlorine splits the O3 into atmospheric oxygen and chlorine monoxide. Two of these chlorine monoxides join together then to form a chlorine peroxide, which then, in the presence of sunlight, get broken apart into atmospheric oxygen and a chlorine atom, and the whole thing starts all over again. So the problem is these CFCs release chlorine atoms high into the atmosphere, and these chlorine atoms basically go through an entire process where they tear apart the ozone into oxygen, and then do it again, and do it again, and do it again. And so that's how they are damaging or lowering the amount of ozone up there in the atmosphere. The ozone layer is thinnest over Antarctica, southern Australia, New Zealand, and South America. So nearer the poles is where it tends to be the thinnest. Ozone levels have decreased about 2 to 10% at mid-latitudes, so that would be closer to where, say, the United States is, during the past 20 years. Ozone depletion causes DNA damage in plants and poor phytoplankton growth because it is allowing a greater amount of ultraviolet radiation to stream through, and that radiation can cause mutations and damage DNA and cause other problems. An international agreement signed in 1987 has reduced CFC usage and resulted in a decrease in ozone depletion. So we're hopeful that since we have, for the most part, stopped using as many of these CFCs, that this ozone layer will over time repair itself. Here you can see the erosion of this ozone shield represented by the dark blue. So here is 1979, and here this big open gap you see in September 2009. This dark blue represents less ozone up there in the atmosphere at the poles, and so that's what we're trying to fix, basically, is this hole. And then there's a reduction over the entire planet, but it's most noticeable there at the poles. So that's another good example of human activity, how it has negatively impacted the overall environment of the world, the biosphere itself. We're going to take a quick break, and then we're going to come back and look at global warming, to kind of look at that separately, just because it's been in such the news lately, and we'll talk just a little bit about the greenhouse gases and the greenhouse effect and what global warming is, or what that term sort of represents, and then we'll finish up with our last couple of concepts. Take a break, be right back.